of the institutes that are using the CCTV cameras for surveillances, and there are plenty of private colleges and schools who are also using the CCTV cameras for surveillances. Now my question is that, will the use of CCTV cameras stop the person from cheating? Okay, or how effective will that be? For example, when in 2015, December 2015, when UP Board of High School and Intermediate Education announced that we are going to install multiple CCTV cameras across for all the examination hall for the board exams. So the principal secretary was asked that, who is going to monitor the CCTV cameras? So, and he mentioned that, the monitoring is not required, the data gets stored in the cloud for a month. Okay, so there will be a flying squad comprised of some teachers and a couple of policemen. So they will be going through the entire video. Okay, and if they figure out that someone is cheating, so that person will be disqualified. So I see two things over here. The first thing is that they are throwing an open challenge that to the students that if you want to cheat at your own risk. If you find out later, so you will be disqualified. But another thing that I see over here is that it's also a tremendously painful job for the flying squads to go through the entire video, which is of 2 to 3 hours length, and figure out who cheated, and that video is being captured from multiple angles. Now you can say that, well, you can fast forward the videos. The cheating movements are so sharp, and that lasts for just few seconds. So if you fast forward that, okay, so basically you miss out a lot of patterns over there. Okay, so when we decided to take this project up, the first thing that we started with is to define cheating. Okay, so we had to define cheating. Okay, so that is, what is the thing, what are the movements that I want my computers to capture? Okay, for example, I may want my computer to capture a person when the person is turning towards the left, or the person is turning towards the right at any inclinations, or the person looking around at the back towards the left or the right. We also needed to ensure one thing, that this model should not be like the usual left or right turn detection algorithms or the models, existing models, because what they do is that even if you slightly turn your face towards the left or right, they detect. And it may happen in an examination that a person may be looking at the left, okay, tilting the head at the top, maybe thinking something, and I don't want my model to bother such movements. Or maybe the person is moving towards the right, taking a pen or looking into the calculator, and I neither want my model to bother such movements. Okay, I only want my model to detect a movement of the face when the face is turning far from the center. Of course, what far is in this case is defined by us. Because the face of a person sitting at the back may get obstructed by the person sitting in the front, or the obstructions may be deliberate as well. Okay, or the face of the person may get out of focus, so the person sitting at the back may get out of focus. Another thing is that when I fix a camera, where should I fix it? That's a big challenge. If I'm sitting it at the center, the person who is writing an examination over here is also already side-faced person for this camera. Okay, so the person will always be detected. Okay, not only that, the movement, angular movement differs. Okay, for the person sitting at the front, for the person sitting at the back, so this differs. So probably this won't be a feasible thing to do. So we decided to use mini cameras fitted or installed at individual desks, and one surveillance camera recording the entire class, so that whatever movement gets recorded by this camera, so if the camera detects that a person is cheating, we will be able to understand that how that person was involved in taking such a move from the other camera. Now, after deciding upon this thing, we made a quick sketch of the idea that what is the thing that we wanted. Okay. And the sketch looked like this, that there will be a desk with a small camera fitted to it. It will be connected to a computer, a small one, not a laptop. Okay, there will be a surveillance camera, will be connected to another computer, and we will find out a way for these two computers to communicate with each other. So this was a diagram that we made like 6-7 weeks back. Okay, now we have the models in action, and I would like to show that how this is working now. So you see that this is the person. Okay, so I don't know whether it's visible properly. So this is the person, okay, who is sitting over here. Okay, so this is the person, and there is a camera fitted over here. It's recording the movement. The camera, which is fitted at the desk, is the one which can detect inappropriate movements. And we are using the other camera to understand how that person is involved in such a movement. So I'm turning on the video. So you see that we can see the motion of that person. Not only that, we're also able to see the other person who is not turning the face but helping the other person to look at his paper. Having decided upon that, we needed to figure out a way to train the computers. That means we had to choose a model. Right? Because computers will need a mathematical framework or a statistical framework to learn this thing. And one of the key to choose the model was to understand how we are capturing the images for detection. So you see that we had a camera fitted for every student, small camera fitted. Okay, and that camera was recording the video continuously, and that frame is capturing only one face. Okay, so there are not multiple faces. So the detection of the face or these movements may not be such a challenging task over there. Okay, so we rather preferred a use of a very simple model. Okay, so there is a model called Viola and Jones object detection algorithm. Okay, invented in the year, and this paper was published in 2001. And literature says that this is the algorithm which made the object detection a reality, a real-time object detection a reality for the first time in 2001. Okay, it's still preferred for its simplicity. Okay, so, and we tested this algorithm on our system and it was working pretty fine. Now, imagine that we were trying to, not in this setup, but imagine that we were trying to detect faces of the people in a street or from a swimming pool. Probably this algorithm would have failed. Okay, for example, we are running another capstone project which involved the detection of suspicious behavior in a store. For example, in the case of emergency, when the person comes in and takes out a gun, points out to the person, or person comes in wearing a mask, people freeze and they are unable to raise alarms. Right, so how about training those CCTV cameras to identify those gun points, a person coming with that mask, to raise an alarm instantly in the real time to the necessary person. So we tested using this Viola and Jones algorithm and it failed miserably because it was giving a lot of false detections. So we had to use some very complex models that has the ability to capture these finite details like CNN and its variants. But here, this Viola and Jones algorithm worked pretty well, and we use this OpenCV library, a very popular one, and the key foundation of this OpenCV library is this Viola and Jones algorithm. And we use this Python as a software. And now, after we have decided upon the model, the next thing is that we need data, to train the model so that my computers get trained for the detection purpose. So when we are saying the computer, you detect the face when the person is turning the face towards the left, I need to tell the computer what I mean by a person turning the face towards the left. So in a way, what I need to do is that I need to capture a lot of images of a person turning towards the left and feed them to the model. My computer or machine learns from it. Now, not only that, we also need to use a lot of negative images so that my computer can discriminate a face from a non-face. So they need to understand what is a face, what is a non-face, and if this is a face, this is turning towards the left. Right, so we collected a lot of images. Now, this is something that we will have a separate session by Akanksha. Okay, we will also have a separate session on the models. Session means over here, will be section on the models as well, that how it works in reality. And now when we had all the models working, okay, we were thinking of how we can make the process automatic, from the start till the end, and finally come up with a dashboard that's useful and helpful, So with our system, you need not go through the entire video of 2 or 3 hour length. We highlight specific minutes and seconds where the cheating-like movement happened. And, for example, this is the person, Priyank, okay, who made a movement at 12:15, turned towards the left for 10 seconds, and there are 2 links to the camera. Okay, so if you can click on this link, okay, so that shows you that how this person was involved in this movement. Okay, so this is the entire flow of the process. Now, one thing we constantly kept asking ourselves is that when we took this project, that will this bring a difference or not? So when I'm talking about will this bring a difference, so I'm actually talking about, you know, making a comparison between the human-based invigilation and the computer-based invigilation. Now that is a very debatable topic though. I will share my thought, but before that I want to take you through a small funny 40-second video of what may happen inside an examination hall. Okay, so I guess that probably all of you have witnessed such incidents in your lifetime. So turn on this video. Yes. So this is a video of where a human is invigilating an exam. Now, this is a very usual case, a very, very usual case. So I showed you this video to make a point. Inside an examination hall, there are constant exchanges of signals. You know, signal emitters by the invigilator and the students. And we are trying to understand from the signals that, is this person going to cheat? Is this person going to turn right or left? So we are always trying to understand that who are more likely to cheat and how they may get involved in cheating. And the students, they are trying to understand how they may get caught, right? So what will happen if I put a machine in action instead of this human invigilator? I will say that this is a machine that's capturing the movement of the face, and this person doesn't know how they're getting captured. Okay. Now, of course, someone is not going to look into each other's paper when a computer is constantly facing at you, okay, focusing on you. But this brings in one difference. The machine doesn't emit any signal. So it gives you no clue that how you're being watched at, right? So it sits silently over there, keeps watching you, and once you make a movement, and the movement that we consider inappropriate, it just detects and records the timestamp and the duration and the action. Right, so kind of we feel that probably if you can kind of reduce the signal levels that were happening inside the examination hall, so probably this might help. This is the general framework of the real-time face detection. So we are capturing a video through the webcams, and feeding through the computer. The computer breaks them into a number of frames, okay, because they can't do the analysis directly on the video. They need to make the analysis on the pictures. And they make the detections, right? So this is the usual frameworks that we will be discussing in this workshop. For a moment, we will talk about the theory, that is this Viola-Jones algorithm and how it works. Then I will call Karthik, Himanshu and Akanksha to talk about the journey that they faced in the project. So they're the one who made their hands dirty in the project. Okay. When the paper was published, it was published by this name: Rapid Object Detection Using a Boosted Cascade of Simple Features. So although the name was object detection, Viola-Jones demonstrated in their paper using a face detection experiment. So that time the face was a frontal orientation face, and all the images were converted to grayscale. And that's what we're going to do. We're going to convert all the images to grayscale, right? A little bit about the image. So when we talk about an image, now, an image is composed of a number of displayable units called pixels. Okay. And each of these pixels are associated with a value called the pixel value. For a typical grayscale images, this value ranges from 0 to 255. 0 means black and 255 means white, and the rest of the numbers are the shades of gray. And for a color image, each of the pixel is a tuple of 3 values. Okay, one for R, for G, and B. Okay, so the RGB image. Okay, so I will give you a simple example over here. For example, here say that we have a 12 cross 16 images. So we have 12 pixels over here and 16 pixels over here. And this face, this kind of resembles a face. Okay, so very rough one. We have the eyes, we have a nose, we have a hair, ear. Okay. And probably you're not able to see the number. I will read something out for you. This number over here, it's a black, the darkest one, and this value corresponds to a 0. Okay, this corresponds to a 2 and a 6. And this number over here is the brightest one. It is 255. This is 241, again 255, 243. And let us see some gray pictures. This is 191. This is 214, 233. So picture is composed of these pixels, and each of the pixel has the pixel values that ranges from 0 to 255. Viola and Jones algorithm, instead of using the pixels directly, they attempt to create some very simple features out of these images called the hard features. This hard feature is a name given due to Alfred Haar because of his work on Haar wavelet that was published somewhere in 1910. Okay, and there are like 3 features that this algorithm attempts to create. One is the age feature, which tries to detect the age of the faces, like the side or the hair, the age. These are the features. The line features, these are the features that attempt to detect lines. For example, so the lines of the face, this region is darker compared to the other regions. And there is a rectangular feature which attempts to detect the diagonal edges. I will give you some example of these features. Let's talk about the age feature. You see that this is a feature. Okay, so that's trying to detect this right edge of this person, this portion, okay. And it's composed of a number of pixels, and each of the pixels are associated with some values. And now each of these hard features are also associated with a value, and the values are calculated in this way. It's the sum of all the pixel values from this rectangle minus the sum of all the pixel values from the right rectangle. Okay, so if we just take the difference, what we get is the feature value of this particular age feature. Now imagine the case that where you have this entire thing as black, means all the values are equal to 0. So the darkest possible area you can have. And all these values are equal to 255, so that is the brightest possible area that you can have. So the value of this feature is going to be 2040. More this value reaches towards this value, more prominent the feature is. Okay. Here is an example of a line feature. You see that this line feature was trying to detect this line, So there is a darker region and 2 less darker region around. So this kind of features are used to detect the lines. Okay. And this feature is also associated with a value, and the value of these features can be calculated by taking the sum of the pixel values of the 2 outer rectangles minus the sum of the pixel values of the inner rectangle. Okay, so in this case we get 1963. The rectangle features can also be found. You see that it's trying to detect this age. Okay. So it can be a larger rectangle as well, not necessarily it has to be a 2x2 rectangle. Okay, and this feature is also associated with a value, and the value can be calculated by taking the sum of the pixel values of these 2 rectangles minus the sum of the pixel values of the other diagonal. Now, here the point is that we can find a lot of these features from an image. It's just not few of them. For example, for a typical size, say let's consider a 24 cross 24 pixel image, we can have like 180,000 such possible features. While most of them are not useful in discriminating a face from a non-face, some of them are really useful in discriminating a face from a non-face. And what Viola and Jones attempts to do is that they attempt to find out those features that will help us to discriminate a facial image from a non-face image. Okay, in this case a face, otherwise an object. The building block of Viola-Jones algorithm are decision stumps. Now those who know about decision tree, a decision stump is nothing but just contains one root and two leaves. Okay, so I will show you. Okay, so if you don't know about decision tree, a decision tree is something that looks like this. So here we will label all the facial images, positive images +1 and the negative images are -1, and the negative images can be any image other than face. Okay, and so it will attempt to find a feature like this out of all those 180,000 features if you're considering a 24 × 24 pixel square size, image size. So it will attempt to find a feature and a threshold value which will best help us to discriminate a face, a +1, from a -1. Okay, so that's what we attempt to do over here. And we also attach a weight to each of these pictures. These weights are the importance, how important this image are to us. And these weights can be small or large. So if we have a large value of weight, that means we are giving more importance to that particular picture. Now, when we're talking about a model, we need to talk about two more things, that the error associated with the model, right? And how important that model is for me. Okay, so if the error associated with the model is less, the importance of the model is high. If the error associated with the model is high, the importance of the model is less. So we will have these two more measures, an error measure and a measure for model importance. Okay, now if you know an indicator, what an indicator function is, probably you're understanding what is going on in this formula, but let me explain that in a very simple way. Suppose that I fit a model and I make a prediction on these images. And it happened that this 1, 2, 3, and 4 images got misclassified. So the error rate associated with that model will be the sum of all these weights. That's the error rate. So if you have a number of pictures and some of them gets misclassified, the error rate associated with the model will be the sum of the weights associated with that picture. And the model importance for this thing, for the model importance, let me show you a graph. And now you see that this is the formula of alpha, which we usually use to denote the importance of a model. Okay. And now this alpha depends on the value of the error rate, which is epsilon in this case. Okay, so we have the error rate. We have plotted this alpha versus this error rate, and we get a curve like this. You see that, note one thing, that when the error rate is very less, it's very less, the model, the importance is very high. In fact, when the error rate tends to 0, this quantity tends to infinity. So a model with absolutely no error is going to have an infinite importance for me, right? And as the error rate is increased, this, we are increasing this kind of to 0.5, you see that importance is 0. Okay, so when we are talking about a model that has an error rate of 0.5, we are talking about a very non-informative model, So it's like you take a coin out of your pocket, you toss the coin, if head turns up, then classify it at face. If tail turns up, then classify it at tail. So it's like a random prediction. Okay, and that those models shouldn't have any importance, right, for the classification. And so this formula sets that importance, the importance of those models to 0 for the error rate at 0.5. Now, as the error rate increases from 0.5 and above, we started to give negative importance to the model. Okay, now this negative importance is really very interesting. I'll show you with the help of an example that why we put a negative importance. Suppose that these are the actual images. Okay, a plus means a face, non-face, non-face, and non-face. These are the actuals. Okay, I pass all these things, images, through my model, and this is what I get as a prediction. A face is predicted as a non-face, another face that was predicted as a non-face. So you see the -1 is predicted as +1. There is only one properly classified example that we have. The rest, everything that we have is misclassified. So this model is associated with huge error rate, right? Now what we are doing is that if we are attaching a negative importance like 1.8 as with this model, what happens is that this minus gets multiplied to this signs of these predicted values. So this minus becomes a plus. This minus also becomes a plus. This plus becomes a minus. Now you see that what I'm doing is that using that negative symbol, I'm just toggling it, and toggling the sign. Now the positive is being predicted as positive. Okay. This positive is also being predicted as positive. The negative is being predicted as a negative, and so on. Right? So we use that negative sign of alpha to toggle the sign so that the prediction improves for a model that is associated with higher error rate. So now, so far, what we talked about is that Viola-Jones algorithm uses decision stumps as their building block, and the decision stumps, they aim to find those features among all those 180,000 features that can best discriminate a face from a non-face. That means such a feature for which the error rate is minimum. Okay. Now those are weak classifier. Now I definitely cannot use one decision stump to make a prediction for this kind of cases. Okay. So and the error rate associated with this kind of things are usually high. So what they aim to do is that they try to combine those decision stumps together to develop a strong classifier. And the combination is done using a boosting algorithm called AdaBoost, or adaptive boosting algorithm. Okay, so what is done over here? So I'll give you a little demonstration. So you see that at the first round of adaptive boosting, what happens? Each of these images are given equal importance. Okay, so every image has the equal importance. Then use a for loop, go through all the 180,000 images, find out that particular feature, hard feature, okay, and a threshold value that will help you to best discriminate a face from a non-face, means for which the error rate is the minimum. Use this model to predict on this data. Okay, you see that these are the 3 images that got misclassified, and the error is nothing but the sum of the values of the weights. So that's precisely what we learned. And the model importance for this model is calculated using that formula. Now how boosting improves the classification performance of the model is that in the next round of boosting, the boosting is an iterative process. Okay. So in the second round of boosting, what it will do is that it will inflate the weights of these observations which got misclassified, and it will decrease the weight of the other images which got classified properly. So the second round of boosting, it will look like this. So we have a higher importance for those pictures which got misclassified. Now again, for the boosting, it will attempt to find another hard feature for which the error rate is minimum. Now understand in this setup, now if you're talking about the error rate is minimum under this setup, then I need to essentially, classify these observations properly, otherwise the error rate is going to be high. Okay, because error rate is calculated by the sum of the weights of the misclassified observations. So we find another hard features like this and a threshold for which the error rate is minimum. Okay, and each of these hard features is associated with a value. Okay, see if you remember. And we calculate the error. Okay, so these are the 3 images that got misclassified. Means 3 negative images got misclassified as positive. And so the error rate will be the sum of these 3 numbers. We got 0.21, and based on that we calculate the model importance. Now the importance or weight of those 3 observations will be increased in the next round of the boosting. Okay, and the other values will decrease, right? And this process, this process continues. Okay, we get another tree, okay, and we calculate the error rate and the model importance associated with that tree. Okay, and it goes on, and finally we combine all these trees, with the model importance values to get a very strong classifier. And the classifier looks like this. So it's the model importance times the predictions made by the first model plus the model importance times the prediction made by the second model plus the model importance of the third model times the prediction made by the third model. And if you do this thing, take the sign of this thing, what I get is a predicted value. For example, let's consider this first, for a particular picture, okay, this first decision stumps predicts a negative, -1. For the second and the third one, it is predicted positive. So we have 0.42 times -1, plus 0.65 times +1, and 0.92 times +1. Okay? Now if I sum this up, what I get is a positive number, right? Okay? So the prediction will be a phase because the number came out to be positive. If the number comes out to be negative, the prediction will be a non-phase. So this is how an adaptive boosting algorithm works. Okay. So now we have this model over there, and let's see how the detection is made. Okay. Now for the detection procedure, we choose a sub-window. Okay. Now one thing, when we feed the images to the model, we are converting the size or downsizing the images to 24 cross 24 pixels. Right. And now when we are reading the image from the camera, the size remains as is. We are not downsizing anything. We are using a window like this. So we have a window, okay. Now this window is trying to attempt to understand whether a face is present in that or not. So what it tries to do, for each of this sub-window, it will check whether the first feature was present or not. The first decision stump that we created is trying to understand whether the first feature is present over there or not. If the first feature is not present, then it rejects the sub-window and it slides, you know. But if the first feature is present in that sub-window, it settles down over here and it checks whether the second feature is present or not. The second feature of the second decision stump, right? Now, if the second feature is present, okay, it's not present, it rejects that sub-window and moves on again. But if the second feature is present, it goes on to check if the third feature is present or not. And this process continues, and this is the process that actually made the detection very fast. So when they written that, so this is rapid object detections. Okay, so the rapid object detection using a cascade of simple features. The simple features are the hard features over here, and the rapid object detection happens because of this region that they have the sub-window. Instead of trying to fit the entire model inside this sub-window and trying to understand whether a face is present over here or not, what it does, it checks one feature at a time, and that feature is not present, it just discards that sub-window right over there and moves on, slides the window to the next one. So it continues this procedure. Now, this Viola and Jones detection algorithm is not this simple, that it's not composed of just one boosting tree with each of them as, as one feature, but it's somehow, it looks like this. Now, before showing you this picture, imagine that each of these things are stages, some kind of stage. And instead of one decision stump at each of this stage, imagine that you have a boosting, an AdaBoost algorithm at each one of these stages. Okay, so it will look like this. So what happens that for one particular sub-window, it will try to figure out whether all these three features are present or not. Okay, if present, then it will go on to check that whether all these features are present or not. If not, it will reject the sub-window right from here. Okay. So this is the fundamentals of this Viola and Jones algorithm. Now we'll come to the very interesting part now. Okay, we're going to talk about the journey. So I'm going to call the students who worked really hard on this project. Okay, worked with the images and the image collections and the experimenting with the models. So that's it from my side for now. Okay, I'll come back a little later. So I'll call Karthik to talk about how we experimented with the model. So what happened when we fitted our first model? Okay, Karthik, yep.
Hello.
Yes.
So, thank you, sir. So, guys, wasn't that easy? So So we started our project by collecting a lot of images. Now, image collection was a huge, humongous task. The process of image collection will be later on explained by my colleague Akanksha. Once we had all the images collected, we started to train our model. Now, model training took around 80 hours to train. Now, with every passing hour, we had a feeling of anxiety, and we had a funny feeling that our model is not going to work. So let's see how our model did not work. So you can see there are a lot of flickers. Our model is detecting almost everything as a face. It's trying to detect the flickers inside the face and the flickers outside as well. But the one positive point here is that it's detecting the left turn correctly. A confusing part is my model is able to find face near the tube light region. So we were wondering what went wrong, why our model is detecting all negatives as positives. So one of the possible reasons is that our model did not have enough negative pattern or enough negative data to learn from. We refit the model, but this time around we gave a number of negative images so that all the negative variations can be learned properly. So let's see the performance of our improved model. So you can see it's detecting the left face correctly, and if you clearly notice, the flickers have reduced considerably. There are no flickers seen in the tube light area. Have been learned. So the thing is, why is our model then detecting the frontal orientation of the face? We thought of that it could be a couple of reasons. While labeling the image during the training process, we had included the hair, the chin portion as well for labeling the detection of the left turn. Now, this is one of the reasons why our model could be getting confused. For the next set of process, we thought of labeling only the portion of the face that actually contained important face-like features. The other thing that we did is that the total images had, all the images that we fed into the model had different inclinations, like front, back, and normal inclinations. Now, this could also be one of the reasons why our model is detecting the frontal orientation as positive. So we created separate models for separate inclinations. Now, after performing a series of such experiments, we came up with our final model in which it will detect a face only when a person turns towards the left, and you won't find any false detections. So let's have a look. So this is what I was speaking about, only labeling the face portion. And it's detecting absolutely perfectly. And we were really happy with the performance of this model. Once our model was ready, we tested our model on 1,000 different images of different people in different inclinations. We could see that our model was able to detect 980 of them correctly. We also tested our model on 1,000 negative images, and all of them were detected correctly by our model. So let me show you an example of how the detection is going on. So here we are using a concept called as Iou. Here it's detecting almost, the detection accuracy is almost 70% for this particular person. For this one, it's 71. So let me show you what the Iou metric means. So Iou stands for intersection over union. So in this case, what we do is we hand label the image saying that where the truth is. The blue one is the rectangle that's predicted by our XML. And Iou is calculated using a very simple formula, that's area of the overlap divided by the area of the union. So using this simple concept, we calculated the Iou and detected the accuracy of our model. Now, generally an IOU rate of greater than 0.5 is considered as a good performing model. So that's it from my side for detection of the models. Now let's call Akanksha, who will be speaking about image collection and processing.
Thank you, Karthik. Thank you, Karthik. So collection of images was an enormous challenging task. Major of our challenges was how do we collect these images in an organized form, process it and label it. So when I'm saying that collecting images in an organized form means we want to collect images of all the left inclination as well as right inclination so that our model don't fail to detect a person when he is turning left or right. Initially, we targeted to collect around 16,000 images. As of now, we have like 20,000 images collected from 30 different volunteers. Let me show you an instance of how we have collected these images. So this is an instance where I am guiding my friend Ruhi to look at a particular word in a paper. So while she was looking at a particular word in a paper, I kept on moving this paper in different directions in a table. So while she was busy looking that particular word, there is a camera here which was constantly capturing her face movements in that laptop. So let's see how this video was captured. So this video was for the normal inclination. Similarly, we captured 3 videos per side: normal inclination, backward inclination and front inclination. As well as at the right side, we had again 3 inclinations. So per volunteer, we had like 6 different images. 6 different videos. So our model don't understand how to process these videos. So we need to convert these videos to frames. Per video, we had like around 100 frames, and per volunteer, we had like around 600 frames. So this is a sample of how these frames we got from those videos. As initially I have said, like we had 30 different volunteers. So this is a few of the images we have captured from our volunteers. You can see we have variations in these images. Some are wearing specs, some are having beard, mustaches, all are having different complexions. So to make our model more generalized, more robust and more flexible, it was very important for us to give all these variations. So let me summarize our journey of how we have collected these images. We captured video clips. Using an algorithm, we captured frames from these video clips. Later on, we have cropped faces from these frames, so that our faces becomes more prominent. Later on, we have resized these images and grayscaled them. Finally, we have labeled these images. So what labeling means? Labeling is a process where I tell my computer where in an image we have face and where are the coordinate captures facial images. So now our images are ready to be fed into a model. So that was our beautiful journey of how we have done our image processing. Let me call my friend Himanshu, and he will tell us how the deployment has done.
How we can deploy this as a product. So let's see how we did this. So this is a setup of a class wherein these are the desks, and we had mini cameras installed in front of each desk which was connected to a computer. And candidate is sitting in front of the desk giving the exam. And at the same time, there is a CCTV camera which is capturing the frame of entire classroom, and this is connected to computer number 2. Now, we used cloud services to have a robust communication between these computers. Now, for the simplest understanding, let's presume that there is a single camera which is there installed on the desk, connected to a computer, and the CCTV camera or surveillance camera, which is capturing the video in computer number 2. Now, as soon as the exam starts, this camera starts capturing the video from the start of the exam till the end of the exam, and simultaneously the surveillance camera is capturing the video for the entire classroom. Also, this computer is keeping a timestamp of cheating-like movement, or if any candidate is trying to cheat over here, it will keep a record of the timestamp, what was the action, that is the candidate turning towards left or right or back, and what was the duration of that particular movement. So as you can see here, that at 12:15, the candidate tried to cheat towards left, and the duration was for 10 seconds. So with the help of these information, the video is being clipped into the small clips where we are only keeping the record of when the candidate was cheating and that particular instance of the video. Once the complete video processing is being completed, this video clips as well as the spreadsheet is being uploaded to the cloud. And let's come to the computer number 2. So after the exam, the same video is there for the entire classroom. So this computer number 2 downloads this spreadsheet, and with the help of the same information of the timestamp as well as the duration, this computer also make the small clips of the moment where the cheating was done, and the same processing is being done for the video being taken for the entire classroom. As the processing is completed, the video files and the spreadsheet is uploaded back into the same folder, and also the original video files for this camera as well as the surveillance camera is uploaded back into the folder. So we have organized the folders in such a manner that for each camera there is a separate folder which have all the files as well as a spreadsheet. And yes, we can definitely scale this for multiple cameras and computers. Now let me show you how our dashboard looks like. So this is a dashboard wherein these are the list of all the students who were giving the exams. We tried to make this very simple with all the information required by any invigilator over here. So let me show you. So as you can see over here, that these are the students, and these are the information for each of the students. So Priyank tried to cheat at 12:15, and as we can see, Akansha tried to cheat at 1 p.m. and she was trying to turn towards the right, and the duration was for 5 seconds. So we also have mentioned the links over here. So as soon as any invigilator click on the link, it will go directly to the cloud services, and it will sorry about that. It goes to this cloud service, and it will open the video over here. And the invigilator can directly see the video over here only for the moment when the cheating was made. So instead of actually checking the entire video for the classroom, the invigilator can check only the videos where the actual cheating was made, and it will make the task very easier for the invigilator. That was from my side, and let's hear from Gourab sir.
Thank you. You take it. Yeah, so this is where the project stands now. So we had this run actually to make this entire thing automatic. So we are giving a starting point to the machine, and we are giving an end point. Okay, so where the recording starts, when the recording stops, the video processing happens. So we pause or make the computer hold for a moment till it uploads all the videos to the cloud, and then make the communication happen, and then the video cropping happens, and then everything is loaded in the folder. Some of the challenges that we are looking at now, okay, so some cases like this, so where the face won't be detected, the person turning towards the left, but with a hand on the face, okay, your algorithm won't be able to understand the thing. or the person standing up, or maybe the person is putting a paper on the camera, right? So the camera gets hidden, okay? Or maybe that hiding the camera by the hand, okay? So the algorithm that we're working now is something that we are calling is as face not found algorithm. So like the way these algorithms are trying to detect a face, that algorithm is trying to find not a face. So if the face is not found for like a threshold of seconds, it kind of will raise an alarm in the real time so that an immediate intervention can be taken place of what's happening over there. Okay, and the recording will happen as usual. Another thing that we are focusing on is cases like this, some cases, okay, I don't know whether we will make the computer help to detect such things, that passing the papers from one bench to another bench, but we can definitely train the surveillance camera to record this kind of movement. So what we can do is that when the images are coming in, I'll just crop these portions of the images and send only these portions in the row and keep a constant focus that what is, if something like this is going on. So probably for this thing, I don't know, we probably may need a setup that kind of look like this, a more controlled setup, So if there are continuous benches, what will happen if the paper is being passed from the bench? So we can't make our computers detect that. So to make the paper pass, to detect the paper passing movement, so we need kind of setups like this. So let's see where this thing goes next. Okay, so that's what we have done so far, and we wanted to share with all of you. Okay, so the students of Praxis Business School and I was the project guide of this project. I will take some questions, so we do have time. Yes? Yeah, come. Yeah.
Hi, I'm Asta. So
Hello.
I have a question that you said that you convert each video into multiple frames. So
Correct.
what was the granularity in terms of time, like 2 seconds? 5
Yes, so
seconds?
what we were doing is that we were capturing 3 videos per second. Sorry, 3 frames per second. Okay, so one of the things is that we were not capturing more than 3. The reason being is that a lot of variations won't be found in that 3. But there was some variations we were finding as lights variation, The light was changing for every frames. So we decided to keep it to 3. Okay, we tried it with 4 as well. That's the maximum that
So what was the size of the data like?
The size of the data, we were working with an image like 20,000 images so far. Yeah, that's the number of images we collected.
Okay.
And each of the images had to be hand labeled. So that was the most difficult task.
Thank you.
Thank you.
Yeah. Hi, this is Shubham. Yeah.
Hi.
So I have a question regarding like what kind of augmentation techniques you considered while processing the images. Like in order to increase the size of the image data that you have, you can perform certain kind of augmentation, right?
No, see, we did not increase the size. You were talking about the size, increasing the size of the data.
Augmentation basically not helps only in increasing the size, but to capture the different variations present in the image data.
Okay, so probably I'm not able to get your questions properly, but I will say that what we were doing is that we only increased the number of images based on the the conversion of video to frame per second. That's what we have done. Okay, so now to capture different variations of the faces and under different lighting conditions, we use different setups. Light setups actually, and so that our model can work robustly under different lighting variations as well. So we kind of right now we are integrating that in a model. We are kind of using some kind of variance transform normalization things.
Okay, and another question I had is regarding the annotation, that when you created the hand label, so it's again very subjective. Let's say a particular.
Correct.
So how basically you handle that kind of a challenge in order to?
Yeah, see, there is no way that by which we can actually make a machine do that, because we are trying to make the machine understand where the face is.
Exactly.
Right. Now, if you even see that, have you heard about that ImageNet?
Yes.
Yeah, Dr. Fei Li of Stanford. Yeah. So when that ImageNet was created, so this review is positive or negative, So they do it for you. So right now that's a big challenge right now. So we need to tell the computer where the face is. So we are the one who need to supervise the computer, right? So this again, it's becoming a supervised learning.
Okay, and the last question I have. So you guys have, based on my understanding, you guys have tried hog feature descriptor basically in order to come up.
Correct.
So have you guys tried with any of the advanced algorithms, namely like YOLO, faster RCNN, Maxed RCNN?
We did not. Yeah, we did not for this project because it's working pretty fine for us. Okay, so as I said that it's just one face being captured by one camera. Okay, so we needed to use simple thing. For the other project that we are doing, I said that detecting the movement in a shop, an emergency movement, we needed to use CNN. But for that's costly. We needed to hire, GPUs. Okay, so we need to say rent the GPUs, from the cloud where we are buying it. So for this, we are not paying any money. So that's the cost optimization. You can say that's something we need to reduce the cost. Thank you so much for the questions here.
Hi, I'm Ritika and I work as an assistant professor. So yes, it was very interesting for me to look at your interaction. I wanted to ask, so basically you've tried to capture about how students do not cheat among themselves. But of course, I believe you've all been students. And since I've been invigilating them, there have been other modes, like they might write something on a piece of paper on their hand in which their face is not changing from the center. Right.
It's absolutely correct. Yeah. So right now we don't have a model that can detect such a thing, but we are kind of considering that a person should not come with a cheat, or they should be thoroughly checked, like the way it happens in GRE, ILTS and CATS. Probably this setup cannot be directly used in colleges and universities under this current setup, unless and until those kind of,
So maybe what I can get is maybe I can use this in a way to aid and help me while invigilating, but I cannot leave the classroom depending upon the camera.
Right now we cannot.
Yeah.
But so maybe, as of now we cannot.
Yeah, but further we can develop upon those.
Further we can definitely develop on this.
Thank you. So much.
We are actually thinking towards that direction because this is a common question that came to us a lot many times.
So please get some data.
Exam from the front for the camera, so it's going to get detected. So the face really differs, right?
We'll take the further questions offline if possible, because there will be a lot of questions. I'm pretty sure there will be a lot of
this is a very debatable topic.
Yeah, a lot of debatable.
Thanks so much. I will be in the stall of Praxis Business School, so feel free to meet me and come with.
Please put your hands together for Gourab, Nath and team. I have also two things to say. Thank you. You didn't create this 5 years ago, or else I wouldn't have, or we wouldn't have passed the stage. And second thing, no matter what you create, students will cheat. Thank you, ladies and gentlemen. You can go ahead for your lunch. The lunch is being served downstairs. You can resume at 1:30 once again for the next workshop. 1:30 sharp will resume for the next workshop. And also we'd like to thank all the sponsors, Analytics Lab, IBM, ZS.
I'll talk to you.
The silver sponsors, Bridge, I2I, Great Learning, International Institute of Digital Technologies, InSafe, ProLearn, Manipal ProLearn, SAP, The Weather Company, Time Professional Learning, Unlimited.
Keep my card.
And exhibit sponsors, 3LOQ, Analytic Treasure Hunt, BDB, Advancer, Idiom, Intelligent Enterprise, Praxis, Reva University, Starcom, and panel sponsor, Actify, All Hands Dinner sponsor, JM Articus.